Hi students, today we will study how we can choose the rating of a capacitor bank in order to improve the power factor of an inductive load to a desired value. In this picture you can see a capacitor bank used with a distribution system. Now we consider an inductive load. So the current I lags behind the voltage by an angle 5 degrees. As you know, this currents can be resolved into two components. This is the horizontal component. It is equal to I cos phi and this is the vertical component, which is equal to I sin phi. As you know, these two sides are equal. So this side is also equal to I sin phi. Now we look at the sides of this triangle. The hypotenuse is I and the two sides of this triangle are I cos phi and I sin phi. Let me draw this triangle separately. And this is your current vector I. The two sides are I cos phi and I sin phi. So this angle is phi. And this triangle is called current triangle. It is current triangle. Now if you multiply the sides of this triangle with the voltage vector, so the sides become VI cos phi and VI sin phi. So this triangle is called the power triangle because the sides of the triangle represents the different power terms. So this is power triangle. You know, this VI is apparent power. So S is equal to VI. What is the unit of apparent power? It is volt amperes. And this is active power, VI cos phi, and its unit is watts. And this is our reactive power, VI sin phi, unit is volt ampere reactive. Now this power triangle can be represented in the simplest form. Let me draw this power triangle once again. This angle is phi. This is our apparent power or volt ampere side. This is our active power side. Its unit is watts. This is our reactive power side. Its unit is volt-ampere reactive. This is also power triangle represented in the simplest form using the units. We know this hypotenuse is apparent power. Its unit is volt-amperes. The other two sides are active power. Its unit is watts. One side is the reactive power. Its unit is volt-ampere reactive. But usually in the power system we deal with high powers. So this can be represented as kilowatts. This is kilovolt amperes. So this is kilovolt ampere reactive. So this is our power triangle in the simplest form. This is the power triangle represented in the simplest form. The sides of the power triangle are redrawn here. This is our main vector, apparent power. It is kVA 1, and this is resolved into two components. One is our active power kW, the other is our reactive power kVAR1. Now this is the initial condition of an inductive load. Now we will see how we can improve the power factor of this inductive load using a capacitor bank. This side is also equal to kVAR1. This is also kVAR1. Now you see the reactive power kVAR1, it is acting downwards because it represents the reactive power drawn by the inductive load. Now suppose we are connecting a capacitor bank. So the capacitor bank supplies reactive power to the system. Suppose this is the reactive power supplied by the capacitor bank. So you can represent this as kVAR C. This is the reactive power supplied by capacitor bank. Now you look at the picture. The reactive power supplied by the capacitor bank is acting upwards, whereas the reactive power drawn by the inductive load kVAR1, it is acting downwards. They are opposite to each other. What is the resultant reactive power required by the load now? Now this is the reactive power supplied by the capacitor bank. This is opposite to the reactive power drawn by the inductive load. Now the resultant reactive power required by the inductive load will be this much. So this is kVAR2. This is the reactive power required by the inductive load now, because the remaining reactive power is supplied by the capacitor bank connector. This is the reactive power required by the inductive load now. Now the reactive power required by our inductive load is kVAR2. So this will be our new kVA2. So this is the reactive power supplied by capacitor bank. So this is our reactive power required by the load now. This is our active power. There is no change in the active power. Initially, what was the requirement? kVAR1. But certain reactive power is supplied by the capacitor bank. Now the new requirement is kVAR2. So this will be our new kVA2. Now this is O, A, B, C. What was our initial requirement? It was AB, kVAR1. What is the reactive power supplied by the capacitor bank? It is BC. The new requirement is only kVAR2. Now kVARC, the reactive power supplied by capacitor bank, is equal to BC, which is equal to AB minus AC. Now AB minus AC can be calculated as, what is AB from the triangle? It is OA into tan phi 1. This is OA into tan phi 1 minus, what is AC? The new angle can be taken as phi 2. So what is AC? AC is equal to OA into tan phi 2. OA is our active power. So this is kW into tan phi 1 minus tan phi 2. What is this phi 1 and phi 2? Phi 1 is the initial angle before the power factor correction. This is the phase angle. Before power factor correction. This is the phase angle before connecting the capacitor bank. What is phi 2? This is the phase angle after connecting the capacitor bank, after power factor correction. So this is a kVARC. The reactive power supplied by the capacitor bank is equal to kW into, that's the active power rating, into tan phi 1 minus tan phi 2. Phi 1 is the phase angle before correction and phi 2 is the phase angle after correction. So this is how we have to choose the capacitor bank. Suppose initially an inductive load is working with a phase angle phi 1. You want to improve the power factor angle to phi 2. If the active power rating of the device is known to you, if the active power rating of your equipment is known to you, using this formula you can calculate the required reactive power supplied by the capacitor bank. So using this formula you can choose the reactive power rating of the capacitor bank in order to improve the power factor to a desired value. Now we consider a 3-phase 50 Hz 80 kW induction motor. It is working with the 0.75 lagging power factor. We need to design a capacitor bank to improve the power factor to 0.95 lagging. How we can design the capacitor bank? kVARC, the reactive power supplied by the capacitor bank, should be equal to kW rating into tan phi 1 minus tan phi 2. What is this phi 1? This is the phase angle before power factor correction. And phi 2 is the phase angle after power factor correction. After the capacitor bank is connected, phi 2 will be the new phase angle. This is equal to, what is our kW rating? It is 80 into, here the tan phi 1 is the tan theta corresponding to our initial phase angle 0.75. Tan phi 1 is equal to tan 41.4 degrees and tan phi 2 is equal to 18.19 degrees. What is the initial power factor? 0.75. We need to improve it to 0.95. So this 41.4 is corresponding to that cos phi 1 is equal to 0.75. From this you can calculate the value of phi 1. And this angle is from, cos phi 2 is equal to 0.95. This is the power factor to which you have to improve using the capacitor bank. If you calculate the value, you will get this kVRC is equal to 44.25 kVR. So this is the capacitor bank we need in order to improve the power factor from 0.75 to 0.95.